In this paper, we investigate the problem of tabletop rearrangements with heterogeneous objects. In rearrangement problems, the robot arm moves objects from start positions to desired goal positions. In general, this problem has two aspects of challenges. On one hand, it needs to deal with the combinatorial challenges, where we want to find a sequence of actions moving the objects to goal positions without collision. On the other hand, when some of these objects cannot move directly to the goal positions, we need to allocate temporary free space to place these objects, and we call the free space buffers. We also notice that in practical rearrangement problems, some objects are small and thin, while others can be bulky. The bulky objects tend to block more objects from their goal positions, but they are also harder to allocate buffers for. So one natural question would be, how can we leverage object properties to guide heterogeneous multi-object rearrangement planning? In this paper, we propose heuristic functions based on the object size and shape. And we also investigate ways to integrate the heuristic function to the combinatorial planner and a Monte Carlo tree search planner. In the combinatorial method TRLB, the general idea is to do sequencing before the buffer allocation. This is similar to the idea of doing task planning first and then search for the motion planning details to make the task plan feasible. TRLB solves the sequencing problem by computing a graph layout problem. In our proposed method, we represent object properties in a weighted graph. By solving instead a weighted graph layout problem, we find the task sequence minimizing the total or maximum difficulty of the buffer allocation process. On the other hand, in Monte Carlo tree search, the branching is controlled by a UCB function. It looks for a balance between exploitation and exploration. In our extended Monte Carlo tree search, we add weights to exploitation term to prioritize actions that's making progress to moving large objects to the goal. In this way, the priority will increase gradually so that it will not be too greedy in the planning process. In our simulation experiments, we test our algorithms in two different scenarios. The row values represents different density levels of the workspace objects. In the rand instances, object shape is randomly chosen. The size and the ratio aspects are also uniformly sampled. In the SQ instances, we mimic the situation where a few objects are significantly larger than others. We conduct extensive experiments, and here are some takeaway conclusions. First, our proposed algorithms have better improvements in SQ instances than rand instances, because SQ instances has more diverse object shape and size. Second, in difficult cases, ETRLB effectively increases the success rates. Finally, both methods are more efficient than baseline in the sparse SQ instances as well. This is a real-world demo for the SQ instances. The first two columns are variants of the TRLB and their extended versions. Objects are only allowed to be placed inside the white paper region. Our method can also solve instances with general shaped objects in a more confined environment. To conclude, first, we investigate the rearrangement planning problem with heterogeneous objects and explore the effects of object properties in long horizon planning process. Second, we propose planners using two different search algorithms for this problem. Finally, with experiments in both simulations and the real world, we demonstrate that taking object heterogeneity into account is beneficial in rearrangement planning process. Thank you for listening.